Well, good morning. This is 9:34 on Wednesday, the 26th of April, 2017. Should be Calculus 2 class, Calculus 1 class, 125. The trouble is I'm the only one in the room, and this is the last day of class. So I was going to be returning papers to you today, but nobody's here to get them. And I was going over the last, how we're going to do things to wrap up the term. And I guess I should make this here for in case any of you don't come in and you do listen to the YouTube video. One thing I've said it every class, but not maybe all of you have been here to hear it, so let me say it again. Please do your student course evaluations. Okay, they have been open for a while. They will be open, I know, through finals week and maybe a little bit past that, but I can't say how long, so I wouldn't bank on it. Try to get them done sooner rather than later. If you want to wait until you see grades and stuff like that, hopefully they'll still be open then, but I would say get them done before finals week is over. I don't know if they'll be closed then, but try to get them done then. So that's number one. Number two, like I said, I was going to return papers to you today and answer any questions you might have on anything you may have missed. Anyone who comes in will still get the papers. If you haven't turned in a paper now, of course, your research paper, I can't return. They periodically ask for samples of student writing. And by the way, this class, supposedly one of my best classes, I've gotten 0 research papers in, and today's the last day not to lose any points. So if I don't get them in today, they will start getting them in tomorrow, say, or Friday or next week. They'll be losing points as you go. So please get them in to me today if possible, if not as soon as possible. Okay? Everyone's turned in test 1. I was going to return all those today because the last person turned them in recently. And the trouble is, nobody's turned in test 2 yet, so I need those in as soon as possible as well. And I'm going to give you your Chapter 4 test, and maybe if we can cover a little bit in Chapter 5, it'll be maybe a question or 2 from 5, and that's going to be the last exam, which you can call the final exam. It'll just cover Chapter 4, and if we get any of Chapter 5. I'm going to give you that today if anyone shows up today. Otherwise, whenever you come in, get your test, okay? Now, let me go over the last thing. Now, once you get your test, you can turn it in to me anytime. You don't have to wait till next week. You can get it to me later today if you want to, tomorrow if you want to, Friday, I'll be on Birmingham campus if you want to, or anytime next week, but I need them by the end of the week. Grades, I think, are due sometime like noon on Monday. I don't want any tests coming in Monday. I need them all in by Friday, and I'd rather not have them come in Friday at 1 o'clock. This is next week, because that means I'm grading all weekend. So please get me your papers. Try to get them to me by the end of business on Thursday, but I will accept them Friday morning. Okay, let me go over my schedule then. Today and tomorrow is pretty much as normal, okay? Friday, however, there's just a very minor change. My wife has professional meetings in Amsterdam, poor gal, next week. She flies out Friday and comes back the following Friday. So I need to take her to the airport. We either need to leave home at 1 or she needs to be at the airport at 1. Whichever, that means I got to leave campus early on Friday. Now, I've put in enough hours already this week that I can easily afford 45 minutes to an hour off, and I don't think there'll be any problem taking it. But I just wanted to let you know, Friday, normally my office hours are on Birmingham West Campus. Normally my office hours are 7:45 until 1, but day after tomorrow, this Friday, I will have to leave either by 12 or 12:15. It depends on whether she needs to be at the airport by 1 or we're going to leave the house at 1. She said last night, but I don't remember which she was talking about, leaving the house or being at the airport. So anyway, I'll need to leave 12 to 12:15 on Friday of this week. Okay, next week. My Monday, Wednesday classes, you're included, are having take-home finals. So I will not be up here in the classroom for any special reason on Monday or Wednesday of next week, because Monday, Wednesday classes, all 4 of you have take-home finals. Now, so that means most of Mondays and Wednesdays I will be in my office pretty much from 7:45 until 5:15. This is next week, final week. The exception to that would be if students come in to do makeups, and that could happen. So good to see somebody here. I was getting a little crazy talking to myself. All right. So let me turn on the light.
Oh, the light on is fine.
Huh?
The light on is fine.
Well, somebody else may come in and might be taking notes. Well, it helps me see a little bit too, because it's really dark in this corner. Now, I was saying earlier, and now that students come in, I can actually do it. The first test, I got the last one in sometime fairly recently and got it graded more recently. What's that? Oh. Is this the second test that you're talking about?
It's something had completely destroyed.
Okay, so let me see it. I don't know if I have a spare copy. If I don't, I do have the master, but I have to make a copy from it. But let me see.
See if I can get maybe right here. It's just as I was about to turn it.
Okay. So far, I've gone right past it. Let me see. I know it's in here. There's test 1. Something has gotten seriously out of order here. My Cal 3, because I use the same book, my Cal 3 test got mixed in with my Cal 2 test. Cal 1 test. So hold on just a minute. I think I've found the culprit. I've gotten rid of it. Okay, here's your test 2. There's test 2. Yeah, I only have the 1 copy. So right after class, don't leave. Remind me, and I'll go down to make a copy. Because all I have is my master. Okay. And then okay. All right. So remind me of that. Ooh, yuck. I don't know if that's where it goes, but that's where it's going. Okay. Now, let me start over. I said some of this on Screencast-O-Matic already, so it'll be out there. But since no one was in the room, I was having to say everything about what's going on. So, today's the last day of class, which means the paper is due today. Research paper? Huh? Today. This is the last day of class, yes. We've had 2. You'll have the one on chapter 4 and maybe a little in 5 if we get it.
Do we have class on Monday?
We don't have class on Monday. I'm pretty sure that's the first day of finals, isn't it? I know. Well, one problem is we've lost a week and a half of class on Monday, Wednesday classes because we started on Tuesday, not a Monday, and then we had Martin Luther King Day was a Monday, and then we had a weather day on a Wednesday. So we are a week and a half fewer classes than what Tuesday, Thursday classes have had. So that's why we didn't quite get as far in chapter. Well, we haven't gotten to chapter 5 yet. Hopefully, we'll get there today. Okay.
Where will we be on Monday?
Okay, Monday is the first day of finals.
So you will be here.
I'll be here all week, but I'm giving you a take-home final on chapter 4 and whatever we cover in chapter 5.
You give me to us on today, right?
Today, yes.
And we come back in and we turn it in.
Yeah, come back anytime next week and turn it in. Yeah. Technically, we would be having the final exam on Wednesday of next week, but you can bring it in any day you want to. You can bring it in today if you want to, if you finish it today. You can bring it in tomorrow. I'll be on Birmingham campus on Friday. You can bring it in any day, Monday through Friday of next week. But please, I'd rather have them all by Thursday. I will accept them on Friday. But Friday I'll be on Birmingham campus, so I don't want to come in here Monday morning and have a bunch of tests and papers slid under my door and final week is over with. So try to get them to me this week. Now, if you're on Birmingham campus on Friday, I'll take them there. Yeah, this is next week. Okay, so let's go over the rest of the term then. Number 1, have you done the student course evaluation yet? No. Okay, try to do that sometime sooner rather than later. Just don't forget about it. Okay. Number 2, like I said, I'll be giving you your last test today. I'm hoping to get your paper today. If I receive your paper tomorrow or later, you're going to be losing points because today was the last day of class, is the last day of class, and this is when the paper was due. I've been talking about it all term, trying to encourage people to get them done, but okay. So, also I need your test too. I'll give it to you, okay, again. Now, I have class today, normal, and class tomorrow, normal, okay? On Friday, I'm on the Birmingham campus most Fridays, 7:45 until 1 most Fridays, office hours. However, tomorrow, my wife has professional meetings, poor gal, in Amsterdam from Friday through Friday. So I need to take her to the airport, and her flight is at 3, but they say be at the airport 2 hours in advance. So we're either going to leave the house at 1 or I have to have her at the airport by 1. So therefore, I can't stay Friday until 1. I will be leaving either 12 or 12:15. Depends on whether we need to be at the airport or at the house by 1 o'clock. So I will be leaving early on Friday, 12 o'clock or 12:15. That's this Friday. What's that?
I'll just see you on Monday to turn my stuff.
Okay. Okay, so that's Friday. We'll be leaving campus early on Friday. However, next week then, it's a little bit strange. Monday and Wednesday classes, all 4 classes have Monday and Wednesday. They're all 4 classes like this. They have take-home tests. So I will not be here in the classroom at all unless students come in to do a makeup test for something else. So most of the time I'll be in my office. That's 265. You know where that is? Okay, 265. Most of the day, Monday and Wednesday. And Monday and Wednesday, 7:45 until 5:15. I'll be here all day. Okay, now, if someone does come in to do a makeup test in one of my other classes, then I could be, what I usually do is I don't come all the way up here to do them. I do it in a classroom that's empty near my office. So that way I can go back and forth to my office as I need to and hear the phone ring and that kind of stuff. So I could be in 263, 256, 261.
I'll be here at about 7:30, 7:45.
In the morning?
Yeah.
Okay, 7:45 I should be here. Okay, but 7:30 I probably won't be here. So if you do get here before me, you can slide whatever work you need under my door. 265. Okay? Not this office, 265. This is not my office anymore. A long time ago it was, but not anymore. So 265. You know where it is. Right? Okay. Now, so Monday and Wednesday should be in the office all day unless people come in and do makeup tests. And then I'll be in some classroom, like I said, 263, 256, 261, 259, 254, 257, or this one. Somewhere in between my office and here. I know this room is open, so I'll be here if nowhere else. But if any of those other classrooms are open, I'll pick one close to me. No, on Fridays. Only on Fridays. Okay. So that's Monday and Wednesday. Tuesday, I have a final exam in this room, basically 8 to 10. Okay? They may actually go over because that class it's a big class, so there are almost always some students who don't finish in time. So I'll be up here as long as I need to be, from 8 to 10. There's no class coming after me, so I'll be here as long as the students need me to be here. Okay? Now, once they're through, I'll be back in my office. Now, Tuesday afternoon, my mini-term class, that's their last day of class. Because mini-term, they continue until the first day next week. So Tuesday afternoon at 1:15, I'll be up here teaching a class. Okay? We'll be finishing one chapter, doing a lab in that chapter, and doing a test. So the odds are I'm not going to be here from 1:15 until 5:45 like normal. They'll probably be through 3, 4, or 5 o'clock. Just depends on how long they take to do the labs and take the tests. Okay? Then after that, I'll be back in my office until 6 o'clock in the evening. That's Tuesday. Wednesday, I've already talked about. Thursday, my Tuesday, Thursday, 9:30 class, they have a take-home too, so I won't be giving a test anytime in the morning unless it's a makeup, and then I'll be in one of those other classrooms or here, somewhere between 265 and 255. Okay? But Thursday afternoon at 1:15, that's when the final is for my mini-term class. And I'll be here in this room as long as it takes. It's not a long final. It'll probably be less than an hour. I'll figure I'll be back in my classroom my office by 2 o'clock anyway. Okay? There are some computer labs. There's on this floor. I don't know any that are all that easily accessible. But down up on the 3rd floor, 360, there is a computer lab. That's the accounting lab. There may be some others up there too. I know that there are, but whether they're open or not, I don't know. Then on the floor just below us, 157, is a computer lab. Now, it's not always open, but there is a computer lab there. And then also the library has a computer lab that's always open. As long as whenever the library's open, it's open. You know where the library is here? It's down on the 1st floor. So go down this half flight of stairs, then take a left, go down one more flight of stairs, then head down the hallway like you're heading down this hallway, but down below. And when you see the glass doors in the middle of the hall, when you go through those, you're in the library. And the first room on the right is a computer lab. Okay? All right.
And you said the paper is 2 pages on or a page?
I recommend 1 to 2 pages. Okay?
On
Any subject that has to do with anything we've covered. That could be people, theories, applications. Yes, anything such as that. Yeah. Okay? All right. Now.
So why do classes, is it because we're graduating or the classes the end is early?
No, what's the question again?
I said, so why is class in this early? Is it because we're graduating or?
You know, I don't know. I wasn't in on the scheduling for this term. It may be that we started in January a little early. I don't remember that we did, but it may have been. It seems like we started.
Last classes in May, they went to like the second week of May, like.
Okay, who is this?
I think last semester I had science class in May, and they went to like the second week in May and stuff.
Okay, I can never remember classes going that long.
I know my classes last me like in May. They never in April.
Right. I think it's just usually, if my memory's right, the last day of class was usually just right in the first few days of May. But because, let's see, today is the 26th. Yeah, the 26th. The 27th is tomorrow, 28th is Friday, 29th is Saturday, the 30th is Sunday, and the 1st of May is next Monday. So if April would have ended something differently, we would have had class at the last, the first day or two of May. It's just the way the calendar works out this time. But next week is finals week. And I've got to go and check this, but I'm pretty sure that's correct. That's what I've been hearing and everything else. I haven't actually looked at the calendar to see. In fact, I guess I could do that now. Let me. That's not what I want. Yuck. I don't know. It's going to be a pain in the neck to. Let's see, maybe, can I show taskbar? Okay, let me do this. I hate to take class time doing this, but because this computer is sort of slow. The system has been awfully slow today. Yuck. Let me try this. Well, okay. Finally, okay. I wondered when this was finally going to come up. I thought maybe it was in the background, that's why I was messing around with that. Let's see if we can get... This is taking forever. This computer is really slow. Think it wouldn't take this much time. Okay, here is the academic calendar. Okay. Month of April. Yep. 28th. Actually, Friday is the last day of class. And actually, final exams start the 29th. Is the final exam for Saturday classes. And then if we go to May, oh, you can't see this, sorry. No students are in the room. I don't remember to turn on I don't usually turn on the projector, and I forgot to turn it on there. Yeah, final exams are May 1st through May 5th. Okay? They actually start Saturday classes have their final. So, yeah, finals are next week. I mean, yeah, next week. The 1st through the 5th. So I'm giving you a take-home final. So anytime you want to bring it in, if you finish it, I want to bring it in today, that's fine. Tomorrow, that's fine. Friday, that's fine. I won't be here Saturday. If you bring it in Saturday or Sunday, slide it under my door. Okay? I'll be here Monday through Thursday of next week, 7:45 to 5:15 on Mondays and Wednesdays. 7:45 to 6 o'clock on Tuesdays and Thursdays. Friday, finals week, I'll be on the Birmingham campus, 7:45 to 1. But I need to have your exams in by that Friday. I'd rather have them in by Thursday, so I can grade them on Friday, because, well, actually, wow, I didn't realize this. I was thinking final grades were due on Monday, say here they're due for they're due on Wednesday the 10th. I'm surprised that it's that late. Okay, so Wednesday the 10th, that's when I have to get the grades in. So even if you turn in your final on Friday, even if you slide it on my door here, I'll have time to grade it Monday and Tuesday. So get it any time next week. Okay. But there's the calendar. That's when finals are. That's the campus website. Okay. So maybe I should have kept that up there, but let me just go over this again. So this Friday, I'll be leaving campus either 12 or 12:15, sometime like that. So I won't be over there until 1 o'clock. Okay. Next week, like I said, Monday and Wednesday, I already said that. Tuesday and Thursday, I already told you Tuesday. Thursday, I'm giving an exam at 1 o'clock or 1:15, somewhere around there. I think they'll be through by 2. So I'll be back in my office until 6 o'clock Thursday evening. Then Friday of next week, I'll be on the Birmingham campus, Birmingham West campus, 7:45 until 1 o'clock. So you can get it to me then if you will and want to. And then I have to have grades in by Wednesday of the next week. So please get me everything sooner rather than later, but by next Friday. Okay? Any other questions then? And do the student course evaluations. All right, now where we left off, we're in chapter 4, applications of derivative, 4.5, L'Hopital's rule. That's the title of it. However, this last part really, well, it doesn't have much to do with L'Hopital's rule, but a little bit. In section 1.6, we asserted that the exponential functions increase more rapidly than the power functions, and that's certainly true. We didn't do 1.6. That was something you probably would have done in pre-calculus algebra if you had done it, but whatever. We'll now prove this by showing that x to the nth, let's see if we, yeah, this is what we're talking about here. Okay, the x to the nth, that's a power function, is a great deal less than e to the x for every exponent n, and this is shown in the figure that we were just looking at. In other words, what we're trying to show is that the limit as x approaches infinity of e to the x over x to the n is infinity for all values of n. Okay? That's what we're trying to show. Okay? In fact, what I think I'll do is just go back to the figure and let that do the talking for us, because we've taken really awful lot of time today going over the other things. Here's what happens. Now, for small x's, x equal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, maybe even 14, 15, somewhere here, x to the nth exceeds e to the x, okay? But once you get past x equal 13, let's say 15, there goes e to the x way up there. 15 to the x, 20 to the x, I mean to the whatever. It goes like this. Now this is x to the 5th. You can use any power there. If it was x squared, e to the x takes off sooner. X to the 5th, it's going to be high pretty for a long time, but after a while, e passes. If you had x to the 20th, that might lead until somewhere here, but then e to the x won't pass it like flying colors. Okay? So, given large enough number, e to the x always is going to, as x goes to infinity, e to the x is always going to be a great deal larger than x to the n for any value of n. Okay? Now you see these values, 1 million, 2 million, 3 million. These are big values here. And see, e to the x just takes off and goes. All right, that's all we're going to do with that. So you want to do the 4.5 preliminary questions. There's 2 of them. It's up to you. Okay, let's do the first one. What is wrong with applying L'Hopital's rule? Let's see if we can get back, okay, to this. What is wrong with applying L'Hopital's rule to this? Let me get my pen color changed. The limit as x approaches 0 of x squared minus 2x over 3x minus 2. They say, what's wrong with applying L'Hopital's rule to that? Can you? I'm sorry?
Don't you factor out the top first?
Okay.
Don't you factor out the top first?
Oh, okay. You could. Not sure it'll do you a lot of good, but certainly you could. And that would be x times x minus 2 over 3x minus 2. Okay. If I were applying L'Hopital's rule, that doesn't really benefit me. I like it better that way. But the question is, can you apply L'Hopital's rule to that limit? Okay? If you do, you'll get a wrong answer. And here's why. The conditions for L'Hopital's rule, the ratio that you're looking at has to come down to either 0 over 0 or infinity over infinity. And if you plug in x equals 0, sure enough, the numerator is 0. What's your denominator? -2. So that limit is 0. You can do that limit without applying L'Hopital's rule, because L'Hopital's rule doesn't even apply there. L'Hopital's rule applies. Let me go back and just show you. The condition for L'Hopital's rule is right here. Assume that f and g are differentiable over, blah, blah, blah. Okay. And either both are 0 or both are infinite. In that problem we just had, the g was not 0 or infinite. So therefore, L'Hopital's rule does not apply unless the functions that you're looking for, and this is going to infinity. The first L'Hopital's rule was this one, as x is approaching a, but still, assume blah, 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 and the f of a and g of a are both equal to 0. If they're not, don't use L'Hopital's rule. Use your limits as you normally do. It's only when you have a 0 over 0, or later we'll do infinity over infinity. That would be fine too. But most of the time it's 0 to 0. That's why you couldn't apply it to this problem, because that's not 0 over 0. It's 0 over -2. L'Hopital's rule doesn't work there. The second question, does L'Hopital's rule apply to this? The limit as x approaches a of f of x times g of x. Ooh, I messed that up. Okay. If f of x and g of x both approach infinity as x approaches a. Okay, that's the question. Does L'Hopital's rule apply then? Does it apply to a product if both of those are going to infinity? And my first gut reaction is no. It would apply to those if f of x was going to 0 and g of x was going to infinity, because then if you did 1 over g of x, it would be going to 0. And then L'Hopital's rule would apply, but not if both of them are going to infinity. So I would say no. Let's see what the back of the book says. This is 4.5. 4.5. The first one was a no because it's not in the form of 0 over 0 and infinity over infinity. And therefore the second one is no also. Okay. So homework exercises here. Do any of the odds 1 through 10, any of the odds 11 through 15, and any of the odds 17 through 53. And then do any of the odds 55 through 71, and then do either 73 or 75 or both. Okay? Now also take a look here to see if there's anything else that you might want to do. You can look at any of those others. I don't see anything. But remember, just in this section alone, who in the world is L'Hopital? You know, how did he develop L'Hopital's rule? Where did it come? How is it used? You could do several paper topics just on this section. Most of the other sections, there's several possibilities in all those too. All right. That done, let's move on to any questions on L'Hopital's rule. Okay, let's move on to 4.6. Okay. 4.6 is talking about graph sketching. I'm sorry. Okay, sure, absolutely. I'm just hard of hearing. I couldn't hear what you said. Okay. All right. In this section, our goal is to sketch graphs using information provided in the first two derivatives, f prime and f double prime. We'll see that a useful sketch can be produced without plotting a large number of points. That sounds good to me. Although nowadays almost all graphs are produced by computers, or in fact the ones in the textbook were, sketching graphs by hand is a useful way of solidifying your understanding of the basic concepts of the chapter. So let's talk about some of the issues here. And this graph really says it pretty well. If your first derivative, what does that tell you? The first derivative tells you the graph is increasing if that first derivative is positive. It tells you it's decreasing if the first derivative is negative. It tells you you are either at a relative maximum, a relative minimum, or some type of transition point if f prime is 0. Okay? Means you have a horizontal tangent line. So basically the first derivative tells you whether the function is increasing or decreasing, or has a potential critical point. All right, now what does the second derivative tell you? Well, if the second derivative is positive, that means you're concave up. That the first derivative is increasing, okay? Meaning that the second derivative, that the function graph is concave up, okay? So it's concave up. Even if the first derivative is increasing, it will be concave up this way. If the first derivative is negative, decreasing, it's still concave up, but just going down. If the second derivative is negative, that means that you're concave down, meaning even if your first derivative is positive and increasing, it's increasing at a slower rate, so it's bending downward. But if your first derivative was negative and going down anyway, that means the second derivative means it's not just a negative first derivative, that first derivative is getting more negative all the time, meaning it's decreasing, meaning that you're concave down that way. So there's the four basic shapes of your functions, and you can tell just by the signs of the first and second derivative which shape it'll be. Now, of course, if the first derivative is 0, you could have a maximum, a minimum, or a inflection point, and your second derivative will then tell you whether it's a maximum or a minimum or an inflection point. And because the second derivative is 0 at inflection points. Okay. So you can get a lot of information just from the first and second derivatives. Now, this book likes to do the plus, 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 minus, minus, plus, or plus, minus, minus. Okay? And if that's helpful to you, if that says it for you, go for it. The first plus is always the first symbol is the first derivative, the second symbol representing the second derivative. So first derivative positive, second derivative positive, increasing and increasing, curving upward. First derivative positive but second derivative negative, increasing but decreasing the rate of increase, so it's concave down. First derivative negative, that means the function is decreasing, but if the second derivative is positive, it's getting less negative all the time, meaning it looks like it's going to bottom out soon, concave up. But if your first derivative is negative, meaning it's decreasing, but the second derivative is negative, meaning it's decreasing at an increasing rate of decrease, you might say decreasing rate, that means that it's concave down and you're heading more negative all the time. So those are your four basic shapes. Now, in graph sketching, we focus on transition points. That's where the basic shape changes due to a sign in either the first derivative, that's the local minimum or maximum, or second derivative, a point of inflection. In this section, the local extrema are indicated by solid dots, and the points of inflection are indicated by green solid squares. Okay? Now, in graph sketching, we must also pay attention to asymptotic behavior, that is any place where x approaches either plus or minus infinity or a vertical asymptote. Okay? So, the next three examples treat polynomials. Polynomials only, and then we'll move on to others. Okay? Recall from section 2.7, the limits at infinity of a polynomial function are always plus or minus infinity. It all depends on what I call the leading term test. What is the degree of that polynomial, that leading term? So in general, the graph of a polynomial wiggles up and down at a finite number of times, but then ultimately what winds up going to positive and negative infinity, both directions. So let's go to the, okay, sorry. This is the slide that I should have shown in the previous, when they were talking about first and second derivatives and that kind of stuff. Okay. Here's a function. Any old kind of function here. Okay. Now you can tell looking at this, your first derivative is negative here, 0 here, positive here, 0 there, negative here, 0 there, 0 there, and positive thereafter. Okay? That is any old function. Now, notice what's happened. Your red dots indicate places your first derivative is 0. Those are called your extrema, your critical points. Here, here, and here. The green squares indicate where your second derivative is 0. What is that? That's, here's the second derivative. You can tell it's concave up. The graph is concave up here, meaning second derivative is positive. Everywhere from there to here, but it becomes negative here. So at that point where it changes from being concave up to concave down, that's an inflection. Okay? So the green square. Concave down all through here until you get to another green square, because past this is concave up again. So that means your second derivative was 0 there. So the second derivative is 0, those are your inflection points. Where your first derivative is 0, those are your critical points. Okay? And those are all called transition points. Okay? Critical point or inflection points. And those depend on your first and second derivatives. Okay, now, this graph shows polynomial functions. Now, that last one may have been a polynomial function too, but they didn't tell us. They said any old function, f. It may not have been, but it looked like it was one. This one is definitely, these three are definitely polynomial functions. Now, this is a review of Math 112. when we talked about end behavior of polynomial functions. I don't know if you remember that. But they tell you this is degree 3. You can't tell that looking at the graph. You can tell it's an odd degree. How you can tell? This is going to negative infinity here, positive infinity there. So you know this is an odd degree. You know it's not degree 1 because that would be a straight line. But this could be degree 3, 5, 7, and on up. Any odd number beyond 1. Okay? The other thing you can tell is your leading coefficient is positive, because as x goes very negative, your function's going negative. X goes very positive, your function's going to be positive. If this had a leading coefficient that was negative, this would be flipped. It would be going like that. Okay. Now, the next one indicates it's at least degree 4. It could be degree 2. Degree 2 would be a parabola. This has another hump in it. But this is degree 4 or greater. It could have been a 6, an 8, a 10, or 12. That would have been fine. But how you can tell is for polynomial functions, they go to infinity. Once you get x is big enough, then they go up. Now, what the book says, it wiggles and squiggles in between. But at the long run, for very negative and very positive, it's going to some infinity. And if both of those infinities are in the same direction, that means it's an even coefficient. The degree is even. This one, because it has 3 changes of direction, it has to be at least degree 4. They tell you it is degree 4. But this also indicates a leading coefficient, a sub 4, has to be positive because this is on the up and up. Okay? Because if your degree is even, your power function is always going to be positive. X to the 4th, x to the 6th, x to the 8th. No matter what number you put in there, positive or negative, that's going to be positive. Okay? Because you have an even number of either positive signs or negative signs, and all those will be positive. But if that a sub 4, the leading coefficient, was negative, that guarantees they're going down and down. This is going up and up, so that means a4 is positive. Now this is at least degree 5. How do you know? You have 4 changes of direction. 4 extreme of that. Okay? And because you do, this has to be at least degree 5. It could have been 7, 8, or 7, 9, or 11, or something higher, but this is at least degree 5, and they say it is. But when x is negative, this is positive. When x is positive, that's negative. That indicates your leading coefficient had to have been negative. Had to have been negative. Otherwise, it would have been more like this. Does that make sense? That's the review of what we did in Math 112 for end behavior of polynomial functions. So let's go to example 1. Let's see if it has a graph. I don't recall that it does. Yeah, it does. Okay, so let's do example 1. Okay, don't even show the graph. Well, let's just do it first. Sketch the graph of f of x is equal to x squared minus 4x plus 3. Let me get my pen. Thought I had it activated. F of x is equal to x squared minus 4x plus 3. Now, sketch the graph of that function. What would be some good points that would help you sketch the graph? The what? Okay, you're going to plug in values. Is that what you meant? Yeah, so that works. Let me give you something a little bit easier. Okay? Let's first go for our intercepts. Remember them? What's true about an x-intercept? Every x-intercept. What do we mean by an x-intercept? Where would be an x-intercept? If you had a function here on this graph, where would be your x-intercepts? On the x-axis. Anywhere that function will cross the x-axis, those would be our x-intercepts, right? Now, what's true about every point on the x-axis? every point on the x-axis. Every point on the whole plane has ordered pair. What's true about one of those features, one of those coordinates of everything on the x-axis? One of those coordinates is always the same on the x-axis. What is 0? Yeah, but what is 0? Okay, if the ordered pair, are both of them 0? If both of them 0, you're right there. Sure enough, that's on the x-axis. Huh? The y is 0, exactly. No matter what your x is here, on the x-axis, the y value is 0. That's how you tell your x-intercept set. And what is your y value in this problem? I don't see a y there. Alpha of x is always y. Remember that. Now, when I teach pre-calculus algebra, that's the first thing I tell them. First thing you need to know about functions, f of x is equal to y. If you remember that, you got most of the functions covered. So, to get your x-intercepts, you set this equal to 0. Now, when you have a quadratic equal to 0, what is your next temptation to do? How? Factor it. If you can factor it. Now, I guarantee you're going to factor this. I do know you can. How would that factor? X minus 3 times? X minus 1, you're right. Then what does this produce? 3 or x equal 1. You just found your two x-intercepts. And here's what they are. 3, 0 and 1, 0. Because remember, the y is always 0. Okay? You just got your x-intercepts. That's going to help us graph the function. Thank you very much. Now, you have one other type of intercept, and what's that? Y-intercept. What's true about a y-intercept? Okay, and what's true about every point on the y-axis? What's the feature of those ordered pairs? Ah, here's some area. All our X chromosomes are here. Where are the Y's, huh? In the middle of the alphabet's here. Where are the extremes? I don't know. Okay. I hate to take more class time to do this, but because you're here, I'm afraid you won't go back and listen to the YouTube video because you're here. So let me go over the important features that we talked about earlier. Number one, student course evaluations are now open. You can do them anytime. Have you done them yet? Okay, please do them before the end of the term. Because at some point they close them. So I know they'll be open through finals week, but I don't know how much longer after that. So please do them this week or next week if possible. Okay? All right, that's number one. Number two, today is the last day of this class. Yes. Which means your research papers are due today. Okay? All right? So please get those to me as soon as possible. If I get it today, you don't lose any points. If I get it tomorrow or later, you start losing points. Okay? So please get it to me. Don't. What's that? The library's open, I don't know how late today, but I know they'll be open at least until 5 or probably even later.
I'm used to using the Birmingham campus. Is it the same way on the Birmingham campus as it is over here? Like I can use that checkmate card thing. I think I print paper.
Okay, what did you call it?
The little card.
Yeah, well, yeah, I'm sure you can use it. If it's usable over there, it's usable here. Yeah.
Okay.
Yeah.
I was just trying to see if they did it the same way.
Yeah. Okay. Okay. So also your second test. Oh, and by the way, I think the first test, did I give you yours? I gave you your first test, didn't I? Okay. Yeah, the last person to turn in the first test got it to me this week, I think it was. Though he dated it much earlier. but I have received them all. So here's your first test I'm returning. If I had your second test, I'd be returning those too. Because I don't have your second test, I can't return those today. Get those to me as soon as possible as well. And then before you leave today, I will give you your last test, which is your final test, final exam. And hopefully we'll get to that today too. Okay. Okay. Today's last day of class. Now, I'll give you your final exam. You can return it anytime you're through with it. If you finish it today, you can turn it in today. If you finish it tomorrow, you can turn it in tomorrow. If you finish it Friday, you can bring it to the Birmingham campus on Friday, West Campus, and I'll be there Friday. Okay, let me tell you a little about that. But basically, it's not due until next week, and that's any time between Monday and Friday of next week. So just get me your last test back any day next week. Okay, I'll give you my hours in just a minute. Before I do that, today is regular day. All my classes meet regular. Tomorrow is a regular class day. All the classes meet regular. So my office hours are the same. Today, 3:15 to 5:15. Tomorrow, 10:45 until 1:15. Friday, I'm on the Birmingham campus. Now, here's a change. Most Fridays, I'm there 7:45 to 1 o'clock. But my wife has professional meetings in Amsterdam, in the Netherlands, and she has to fly out Friday. And because we don't want to leave our car at the airport all week, I'm going to take her to the airport. And she either we're going to leave home at 1 or she has to be at the airport at 1. I don't remember which it is. Whichever way it is, I'm going to have to leave campus early this Friday. So I'll be over there at 7:45 until around 12 or 12:15. Not past, because I got to get her to the airport. Now, I've worked late every night this week so far, so I've made up more than an hour so far, so I'm okay. So I will be not on campus much past 12 on Friday, Birmingham, West Campus. So next week, Monday and Wednesday, all 4 classes I teach Monday and Wednesday, they have take-home finals just like you do. So I will not be up here in the classroom at all unless someone comes in to do makeup work. That's in any of my classes. If they do, then I'll be in whatever room is closest to my office. I'll try to be in 263 or 256 or 261 or 254 or 259 or 257 or here. Some room between my office and here, 255 to 265, somewhere in there I'll be if anyone comes in to do makeup work. Other than that, I'll be in my office. So try my office first. If I'm not there, try all the classrooms between there and here. If I'm not in any of those, that means I just stepped out to the restroom, to the registrar's office or somewhere. I'll be back in just a few minutes. That's Monday and Wednesday. Tuesday of next week, I have a final basically 8 to 10. So I'll be up here from 8 to 10 on Tuesday. Maybe even later because that class is a big class and it may take longer to do the final. Then on Tuesday afternoon, I've got my regular mini-term class. We have class that Tuesday, so it'll be 1:15 until class is over. Most days we go to 5:45, but we don't have as much to do Tuesday as we'll have normally because we're almost through. So probably we'll be through by 3, 4, or 5 o'clock, something like that. But otherwise, I'm in class up until then I'll be in my office, okay? Then Wednesday, okay, I'll be here till 6 o'clock on Tuesday, probably in my office most of that time. Wednesday, I already talked about being in my office most of the day. Thursday, I don't have any finals in the morning, but in the afternoon, I have the final for that 1:15 class. So they can start as early as 1, and they'll probably be done by 2 because it's not a very long final. So after that, I'll be in my office. What I'm going to give you today is your last test, which is your final test. And it's just going to cover Chapter 4 and maybe a little bit of 5 if we get there. So far, we're not making good progress toward that. Okay. That's Thursday of next week. Friday of next week, I'll be on the Birmingham campus, 7:45 to 1, I think. Karen flies back, but I think it's later in the afternoon, so I won't have any problem getting into the airport there. All right. Now, please try to get me everything next week. This week, if possible, except for the final. I wouldn't press that, but but next week, get me everything, including your final, Monday through Friday. Monday through Thursday, I'm here. Friday, I'm there. Okay. Now, I looked at the calendar. I thought grades were due Monday at noon. They're actually due Wednesday at noon of that week after finals. So that means if you get me a final exam on Friday afternoon at 1 o'clock, I'll still have time to grade it Monday and Tuesday. So there's no problem there. Okay. So get me all your stuff by then. Okay. We will be here. Okay. Let me back up here. Maybe you need to know this too. I forgot about this. It won't mess up Friday at all next week. We've got a family graduation at Auburn on that Saturday, but we won't be leaving until after I beat. I'll pick up Karen from the airport, and we're heading down to Montgomery. We're going to spend the night in Montgomery. Or at least that was the plans. Now, I think we're going to be so late that we may just leave Saturday morning. Anyway, that won't bother y'all any. However, that next week, we have another family graduation at LSU. So we're going to have to leave on Thursday. So I will not be on campus Thursday or Friday of that week after final exams. Okay, we are supposed to be here, but I won't be here. Are y'all graduating? Okay, I will miss your graduation because we're going to be driving back from LSU that Saturday. So I won't be here for your graduation. Sorry about that. Congratulations. Okay. I hope that covers everything. All right, we were doing this example. F of x is equal to x squared plus minus 4x plus 3. We're going to graph it. That's what they said to do, sketch the graph of that function. And I suggested, now, Nicole or Kim, whatever you go by, suggested that we start plugging in points, and that's perfectly fine to do that. But I said, really good points to use are your intercepts. Which intercepts? Well, you have x-intercepts and y-intercepts. X-intercepts are where y is equal to 0, and f of x is always y. So we set that equal to 0, factored it, and found the x-intercepts. The next question was, where are your y-intercepts? And which you prefer going by? Give me a name. Kim, okay. Kim said, where I asked, where is your y-intercept? And you said what? On the y-axis, where what's always true on the y-axis? Every point on the y-axis. About your ordered pairs. Every point has something in common on the y-axis. X is equal to 0, of course. So, guess what we do to that function if x is equal to 0? We plug in a 0. And what does that give us? You can look at it. Oh, you need your glasses. Oh, okay. If x is equal to 0, yes, that's 0, 3. The function is equal to 3. So that gives you your y-intercept of being 0, 3. That's a great start for finding the graph of the function. So let's do it. I won't need it there, I don't think. Let me change. Put the x-axis down there. I think you'll see it in just a minute. I feel like I've done something wrong here, and but everything looks right. But it's not right. Yeah, it is. Yeah, it's fine. Okay. I probably did the axis too far down, though. Sorry about that. I went down too low. Let me go there. Okay. Now I'm going to tick off some points. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7, 8. I don't draw very good points, by the way. Okay. There's our function. Help me plot those 3 points we know. Second? 0, 3. How do I do that? Up 3. Exactly. Other 2 points? Okay, right 3, 0, and right 1, 0. All right, got it. Now, that gives us 3 points. Let's play around with those. Now, we could, like Nicole said, start plugging in other values, okay? But let's use what we just learned. First, about our first derivatives. What is your first derivative of this one? F prime of x is what? 2x minus 4. Now, what are we interested in here? Where the first derivative is positive and negative, so let's start with 0. Let's set that equal to 0. Now, what's the value when x is equal, when the first derivative is 0? Well, one thing you could do, no, first derivative, not where x is 0, but where the first derivative is 0. So that would be 2x is equal to 4, x is equal to 2. Okay, at x equal 2, your first derivative is 0. Okay, that's important to know. So, so this is what we call a critical point, right? Where the first derivative is 0 or undefined. Polynomial functions are defined everywhere. So there's your critical point. So let's go back to our function here and plug in x equal 2. And this is what Nicole said to do anyway, plug in numbers. So let's plug in x equal 2. And what would that be? Okay, you'd have a 4 minus, plug in 2. 4 minus 8, right? Plugging in, yeah, plus 3. And what would that give us? Second? Not quite.
No.
You're
Okay.
Okay. Do your positives. They add to 7. Minus 8 is negative 1. Okay. So f of 2 is negative 1. Well, there's your f of 2. There's your 2. There's your negative 1. There's another point. And this one, we know something. The first derivative is 0 there. Horizontal tangent line. Okay. This is beginning to take shape pretty well. Okay. Now, let's do our, like you were suggesting, let's figure out what values they are at these other 3 points. Our first derivative here at 0, 3, if you plug in a 0 here, what do you get? Negative 4. So that means you have a pretty steep slope here. Negative 4. Wow. That's your derivative there. How about at 1, 0? What's your slope here? Plug in a 1 here, and you get negative 2. So your slope here is not as steep, but it's still fairly steep. That's negative 2. There your slope is 0. How about at 3? Let's plug in 3 here. And what do you get? Positive 2. Very good. So over here we have a positive slope. Now, it looks like to me, yes, that it's negative everywhere back here, 0 here, and positive everywhere there. So yeah, I think I know what this is going to look like. We know what the graph of this looks like, don't we? It's parabola. Exactly. And in fact, because this is what they call our axis of symmetry here, where the vertex is, this is your vertex at 2, 1 is your vertex. Your axis of symmetry, so therefore, since this is 0, 3 over here at 1, 2, 3, 4, you're going to have 4, 3. You can plug that in and see, and I bet you're going to have a positive 4 slope there too. So yeah, this is looking like this. And you can plug in a few more points if you want to. But before we do that, let's do the other thing. Let's do what F double prime is. And what's F double prime? If that's F prime, what's F double prime? 2. That means it's concave up everywhere. Okay? So sure enough, that fits the mold that your function is looking like that. Sure enough. I may not have the points right, but that's what it's looking like. Concave up everywhere. First derivative, negative anything less than 2, positive anything greater than 2. So that's a parabola. 0 at 2, 2, 1. So yeah, you've got everything you need to know there. So let's see. They said the interval from negative infinity to 2, your F prime is negative. Okay? Everywhere from 2 to positive infinity, the F prime is positive. Never changes. Okay? Because there's only one 0 there. So it's going to be negative to the left, positive to the right, or vice versa. So once you find them, you know it's like that. Okay. So let's see. There, sure enough, is our graph. This is your critical point, a local minimum. I should have done a little red dot there. There is no point of inflection because your second derivative is never 0. Okay? So your only critical point was right there. First derivative equals 0. Your points of inflection are where second derivative is equal to 0. Okay. That one was pretty easy, wasn't it? We knew how to do polynomials, or quadratics. But let's move to a cubic. Okay? Now, sketch the graph of this one. F of x is equal to 1/3 x cubed minus 1/2 x squared minus 2x plus 3. Okay? This is on the top of page, or let's see, it's top part of page 232. Chapter 4, section 4.6, graph sketching in asymptotes. See it? Okay. Now, the last time we looked for x-intercepts first. I don't think I want to do that here. Okay? Number one, I can't factor cubics very well, especially if the coefficients are fractional forms. Boo hiss. I don't even want to go there. However, there is one point that's real easy to get, and what's that? X-intercepts are not very easy, in fact, very difficult in this problem. But guess what? That is easy. I don't want to. If you want to, go ahead. Okay, I'll let you do it. Okay? Okay? But, what is an easy point to figure? Okay, 1 isn't bad if you like to add fractions. Okay, I know you do. Okay, we're going to get to the derivative in a minute. But while we've got the function there, what's a really easy point to pick up? What's the simplest number to multiply or add or raise the powers? The easiest number. 1's pretty easy. This one's even easier. 0! What's true about x equals 0? What's that going to give you? It's going to give you your y-intercept. Remember? Set x equals 0. And it's real easy to do. When x equals 0, what's your y? 3. Here's a point right there. So your y-intercept is 0, 3. I say don't ignore these little cheap values. Real easy to get. Now what you suggested, let's do your first derivative. And fortunately things are going to be very nice here. What happens here? One is the coefficient. Right. Yes, is the coefficient. X squared. Exactly. Minus x minus 2. All right, sure enough, I like that first derivative much better when I do the function, don't you? Okay. But what we want to know where your first derivative is, we want to know where that's equal to 0. So guess what we got to do again? But this is much easier to factor. X minus 1 times x, say again? X plus 1 times, I don't know, I may have misunderstood you. Okay, do you want me to show you how I do factoring? You don't have to do it this way, but here's how I do factoring. Okay, first thing I unfoil it. Okay, I don't know if you think of it that way. What's the only possible factorization for x squared? X times x. Then I'll look at the sign of the last term. It's a minus. What does that tell you about these two signs? Opposite, 1 plus and 1 minus. So put them in. Well, I don't care which one you put where, plus and minus. Okay, now, we want what's the only possible factorization for 2? Huh? 2 times 1, right? And with the larger number being negative. So put the 2 here and the 1 there. Now, that may not be correct, but let's try it. You can always check it by foiling. Okay? X times x is x squared. Minus 2x plus x would be minus x. Minus 2, yes, that works. What does that tell you? Okay. X equals minus 1. X equals 2. So, these are going to be your x values of your critical points, right? Where the first derivative is 0. That's what we just did. So to find out what value they are, we plug them in here. Kind of boo-hiss, but let's see what we get. F of minus 1 would be 1/3, and minus 1 cubed minus 1/2 times minus 1 squared minus 2 times minus 1 plus 3. Okay, Nicole likes her fraction, so or Kim likes the fraction. Let's see what we get. What's negative 1 cubed? Negative, okay? So that would be negative 1/3, and negative 1 squared would be positive 1. So that would be a minus 1/2, and negative 2 times negative 1 is plus 2 plus 3. All right, here's the fraction part. Least common denominator is 6, so this will be minus 2/6 minus 3/6, right? So that's minus 5/6 plus 5. So that would be 4 1/6, right? Boo-hiss, but that's the y value. So when x equals minus 1, you got 4 1/6 as your y. Let's do the, x equals 2. Now we got to plug in here again. F of 2 would be 1/3, boo-hiss, times 2 cubed minus 1/2 times 2 squared minus 2 times 2 plus 3. So this will be what? It's 2 cubed. Nope. 8. So this will be 8 cubed, 8 thirds, minus 2. 4 halves would be minus 2. This will be minus 4 plus 3. All right. So okay, let's write what this is. This is 2 and 1 and 2/3, right? 8 thirds is 2 and 2/3, right? Okay. So you got 5 and 2/3 minus 6. Isn't that minus 1/3? Five and 2/3 minus 6 takes you all the way back to 0 plus another 1/3. Okay. So there we have our second point. Our second critical point is 2 negative 1/3. Boo hiss, I don't like those fractions. All right. Now, let's do our graph. All right. Tick off a few points. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7, 8. Okay. Positive 1, 2, 3, 4, 5. Negative 1, 2, 3, 4, 5. Okay. Something like that. Okay. Let's put our points in. 0, 3, 1, 2, 3. That may be not scaled very well, but there's 0, 3. And then we know this one critical point is minus 1, 4, and a 6. There's 4 and a 6, so it's going to be somewhere about there, approximately. Okay? What is wrong with that? Okay, there we go. And our second critical point is going to be at 2 negative 1/3. That's going to be somewhere about there. Now this being a critical point, you know it's got a horizontal derivative. This is a critical point. That's a horizontal derivative. I think we can figure out what's going on here. This must be, and by the way, that's a cubic function, right? So that means it's going to start low and end high because your coefficient, leading coefficient, is positive. So that means we're going to start over here somewhere. Now, I don't know exactly how it's going to do. Probably something like this, and something like this, and something like that. Okay? So you did have 3 x-intercepts. Boy, what a pain in the neck to find those. Okay? Let's just draw them in. I think that's how the function's going to look. Don't you? Because you know the y-intercept is there. You know that. That's easy. You know your critical point there and there. That means a max and a min. And the end behavior's got to be down. Let's see. Let me do it for you. Down and up. So it's got to go like that. Right? Not much choice. And what did we do? We plotted our max, our min, and the y-intercept, and we had the function pretty much graphed the way it needed to be. Now, here's some checks. I'm sorry, I shouldn't have done that. We need to do our first derivative. We did it right here. Let's look at some values. Okay? Our x's were minus 1, 0. Let's go on and plug in 0 here. What's f prime of 0? Here's our f prime. F prime of 0 would be negative 2. That means your slope here is down pretty steep. Yeah, that looks right. Okay? Yeah, I'll buy that. So we've got our point in between the two. Let's do our first derivative at a point over here like negative 2. Okay? So let's do f prime of negative 2, and that's going to be negative 2 squared minus a negative 2 minus 2. What's negative 2 squared? 4. Minus a minus 2 is? Minus a minus 2 is? Plus 2 minus 2. Those two go out. So our derivative here is a plus 4. Wherever that happens to be, it's a plus 4. Very steep. Okay? Yep, that's fitting okay. Let's go over here to, say, 3. F prime of 3, picking some point on the other side of your critical point. What would that be? That would be 3 squared minus 3 minus 2. What's 3 squared? 9 minus 5 equal 4. So over here, your first derivative is plus 4. Yeah, I think we got it right. Increasing up to your critical point, decreasing between your critical points, increasing afterwards. But let's check it. Let's check it by doing our second derivative. What is f double prime? 2x minus 1. Right. And guess what we're going to do? Set that equal to 0 to find our points of inflection, where it changes its concavity. Okay? And what would that give you? You may be saying it right, I can't hear. Right, x equal 1/2. Okay? So we know x equal 1/2, so let's plug that into our original function. Ooh, boo hiss. F of 1/2, this is your F, and that's equal to 1/3 times, 1/2 cubed, right? A big boo hiss, okay? Minus 1/2 times 1/2 squared, minus 2 times a 1/2 plus 3. Okay? Let's see what that gives us. 1/3, what's 1/2 cubed? Nope. You're adding them. You cube it. One half times 1/2. 1/4 times another 1/2 is 1/8, exactly. Okay. Minus 1/2 times, what's 1/2 squared? 1/4. And this will be minus 2 times 1/2 is minus 1 plus 3. Okay. This is going to be 1/24 minus, no, 1/8. 2 times 4 is 8. Okay. Minus, or let's just make that a plus 2, right? All right, I need least common denominator here, 24. This will be 1/24 minus 3/24 plus 2. That would be minus 2/24, which is minus 1/12, right? Plus 2. So minus 1/12 plus 2, that's going to be 1 11/12. Ugh. Okay. So at positive 1/2, go up here 1 and almost to 2. 11/12. Somewhere right there. So there is, whoops, another point here. And this is the point, and I'm going to do it the way the book did. A green square there. That's going to be our point of inflection. And I really should do our critical points as the red dots. Okay? Now we got it. Okay? That means, now we can do some test points here. Let's do x equal 1. for our second derivative. Second derivative, plug in x equal 1. Let me get back to dark. F double prime of 1, what would that be? Yeah, that would be 1. So that means positive. Oh, I'm sorry, I meant negative 1. Sorry. What would that be? Negative 1. But no, negative 3. You're right. Negative 3. Meaning it's concave down. Sure enough, it's concave down everywhere from negative infinity up to where it's 0. 0 right there. Let's try this point here at 2. What is f double prime of 2? And that would be, yeah, positive 3. So it's concave up everywhere from your point of inflection. That's what the green dot is, point of inflection from there on. Concave down here, concave up there, 0 there. Critical point there and there, increasing, decreasing, increasing. You've got all the information you need. Now, sure, we had to plug in some weird points. So I think Nicole would have agreed. Well, I don't know. Anything you plug into that function there is going to have fractions in it. So nothing's going to be very pretty. Okay.
We did my last time, it was like, it looks the same, like as far as that being one problem. This is just one problem.
Yeah.
So it's like this how
Yeah. So I'm on a very small screen here, so I have to crowd it in. If I was writing on the board, you'd see it all. Yeah, but then you wouldn't be saved, okay? And you couldn't go back and look at it later. All right, does that make sense? And that's how you do the problem. You determine the intervals. What do we use to do the intervals? Well, number one, get that y-intercept. It's so easy to get. There's no reason not to, okay? If you can factor the thing, get your x-intercepts as well. This one wasn't factorable, so I didn't even try. Well, it may have been factorable. I didn't want to look at it. Okay. Then take your first derivative and then factor that to find out what, set it equal to 0. That's going to give you your critical points. And factor that to see where they are. But then you have to plug those x values back into the original function to get the y values. And at that point, you have 3 points. Your one critical point, your y-intercept, and the second critical point. Okay? Now, you can plug into that first derivative a value to the left of your first critical point to see what your slope is there, positive always. Anything to the right of the critical point, 0, is really easy. Okay? And that told you it was decreasing there, and then plug in a point to the right of the last critical point, and you got the positive number, so you knew it was increasing from there on. So you got the general shape of it then. Then we do our second derivative, set n equals 0. That tells you the x value where your point of inflection is, where you change concavity from whichever. So you plug that into your function to get the y value. That gives you your green dot there, which is your point of inflection. And then you test what it is on either side of that, and a really easy point. Well, easy point would have been 0 here. If you'd have chosen 0 there, it would have been -1. So you know it's concave down to the left of the point of inflection. And then you could have plugged in a 1 there, and that would have been even easier. That would be a +1, so you know it's concave up from there on. So, sure enough, you got your shape of your function graph. You may not have the points in exactly the right place, but you got the basic shape well. Make sense? Okay. That was example 2. All right. Let's clear the screen and see what they do on it. I think they do pretty much the same thing we did. they did their intervals from negative infinity to negative 1. That's where your first derivative was 0. And then from negative 1 to 2, that's where between the two zeros, and from 2 to positive infinity. Pick a point to the left of this one, like negative 2, a test value. The first derivative is positive there, so you know it's increasing everything up to that critical point of 0, which is at negative 1. Pick a point in between the two. 0 is the easiest one. Your first derivative is negative 2 there, meaning it's going downhill there. Yes, sir. Finished the test already, huh? Two and three. I mean, 3 and 4. Actually. What's that?
Differential test number 1. We're still looking at differential test number 1.
Differential. Oh, I see. This is differential. Okay, got it. Okay, got it. Okay. So basically, they use your critical points to split up your graph into intervals. To the left of the first, in between the two, and to the right of the second. Okay? And then they do a test value for each place, negative 2, 0, positive 3, and see what the sign of these are, plus, minus, plus. So basically that gives you the shape of the graph right there. Okay? Then with the second derivative, you found out that point of inflection was x equals 0. So you do something to the left of that, something to the right of that. I mean, x equals 1/2. Something to the left and to the right. Well, to the left of 1/2 is 0. That was real easy to do. To the right of 1/2 was 1. That was easy to do. You see it's concave down to the left, concave up to the right. So sure enough, that's your graph. And your point of inflection was 1/2, and we figured out what value that was. Okay. I think we're ready for word. Yeah, okay. This is going back. Here's your local maximum here. Point of inflection here. Local minimum was here. Okay? And then they do their signs. Their first derivative is positive, second derivative is negative, so it's concave down. But increasing concave down. Here is decreasing concave down. Here it's the concavity is 0. So up here it's decreasing still, but concave up. And now it's past your second point. It's increasing but concave up. So they like to do the plus minuses, minus pluses, and those kind of things. But, I mean, use them if they help you. We had already talked about all that. I didn't see any reason to do it again. But anyway, that's done. Now, this is a lot of mess so far here. What this is part of this problem here. F of x is equal to, no it isn't. Oh. This is the one we just did. Okay? -1, we're at 25/6. We already figured what that was. 3, 0, we got that one. 1/2 was at 1 and 11/12, which is 23/12. And here was -2 and -1/3. Those were the 4 points we knew. Max, y-intercept, point of inflection, minimum. Okay? Now, you know it's a plus minus here, meaning increasing function concave down, decreasing function concave down, decreasing function concave up, increasing function concave up. Those are how those shapes look. Plug them in here, and you got it. Okay? And we know the end behavior going down to the left, up to the right. So that's fine. Okay. You can't tell me we're out of time already. Okay, sorry about that. Let me give you your final exam then. Okay, I know it's in here somewhere. Okay. Kim, Nicole, whatever, got to make a copy of that for you. Okay. And you're still working on your second test? Oh, you got it. Good deal. Thank you. Okay. Somewhere in here. Ha, here it is. Okay. Either of you need graphic. You would? Okay. No, I've got some in here. Just gotta find it.
And I'm gonna go print this on Thursday, but it's gonna be in here. I ain't gonna be in the office.
I'm gonna be in my office until noon, and then I'm back up here.
Yeah, it's gonna be like a second.
Okay. Yeah. I've got to run to the restroom and that kind of stuff. But if I'm not in my office, you can slide out in my door. It'll be fine. Oh, here it is. And let's see. I've got exactly 2 pieces. Now, let's take a look at this test before we get too carried away. I just had it, and now I've lost it. I just want to make sure we've done everything in it. Now, that first question is a bit bizarre, okay? This is out of the test bank. And basically, if you go back and do that linear approximation, I think you can estimate the roots from there, okay? And you might say, where in the world does square root of x come from there? What's that? On the what? Okay. That one?
That's different. No, the other.
Oh.
Yeah.
Oh, that. Okay. Sorry. Okay. Now. Yeah. If you were to do obviously you can't factor that, right? That's not factorable. If you did the quadratic formula for it, you're going to come up with minus 5 plus or minus the square root of 25 minus 8, the square root of 13 over 2. Yeah, right? Now, if I said that right, the square root of 13 is basically going to be what you're doing. So you estimate, use if you do your linear approximation for f of x, square root of x, and then move toward plus or minus root 13, I think you're going to see that's how you go to that. That's what it's suggesting for you to do. Okay? Now, number 2, I don't remember the book calling them capital M and little m, but basically your maximum value, your minimum value on an interval. Okay, remember how we did that? You did derivatives, and then you said it either equals 0 or undefined, and you looked at the endpoints and those, and you find your absolute max and absolute min. That's what capital M and little m are. You do that for those two. Okay? Same thing for number 3. And we did something like number 4, mean value theorem. That was back in 4.1, I think. And basically, number 5, you'll see that if you plug in x equal to pi eighths, okay, you get pi eighths minus sine of pi fourths I'm sorry, well, I'll let you, yeah, pi fourths, sine of pi fourths. You can play around with that function and get the values that you're looking for there. So if you start playing with that, you'll see how easy that turns out. Number 6, find the intervals for its functions concave up and concave down. You know how to do that, right? Okay. And I don't have page. Here's page 2. Find the intervals for the functions concave. That number 7, same way. And compute the following limits. Looks a lot like L'Hopital rule, doesn't it? So 8 and 9 are that, and number 10 is the graph right here. Now, what we didn't get to do today is do vertical asymptotes and stuff, but guess what? Y'all did that back in. But actually, this one doesn't have any. I'll give you that. But you can sketch the graph of this. Now, if you have vertical asymptotes, list those. I think you'll find you don't. But horizontal asymptote, you will. Local extrema, that's your max and min, and points of inflection. So you know how to do all that, right? Okay. So I think you can do all 10 of those. All right. Good deal. Please do your student course evaluations, and what really hurt us in this course